A liquid of bulk modulus B is filled in a spherical tank of negligible heat expansion coefficient. Its radius is r and the wall thickness is t. When the temperature of liquid is raised by T, the tensile stress developed in the walls of the tank. What is that negligible heat expansion coefficient of what? Of the liquid or of the tank? I think the language should be very, very important here. No, there's a tank. So this is the spherical tank it is. It's a sphere only. So now let R be the radius of it. Okay, first actually, what is actually the situation? The situation is like this. There's a tank. Okay, fine. So inside, let's assume there's a liquid. Thickness of tank is how much? T. So radius is R, thickness is T. Gamma is for the liquid. Is it okay? A liquid of volume thermal expansion coefficient gamma, and bulk modulus is again for liquid. This is a liquid. This is a tank. Able to understand now? No, initially it's a temperature. I will rise the temperature. As I rise the temperature, the liquid wants to expand. So as the liquid wants to expand, so what it does, it wants to expand. This tank will not permit. No, so how the liquid will exert force. So this is at initial temperature. So like you can call rise it by theta. So initially, if the liquid is raised by theta is telling. So initial temperature, let's say that theta 1 degree Celsius. The same diagram. So what liquid? This is at theta 1 degree Celsius. No, it's at natural. The volume of the liquid at theta 1 is 4 by 3 pi r cube. When you rise temperature, the liquid wants to expand. What this a tank will not permit. I would understand, no? So will there be any force exerted by liquid on the tank? Yes, it is. How it will exert force? It will exert force radially outward. This is what arrows here to show it. The liquid will exert force on this tank radially outward. No. So what will happen to tank? Yes, the tensile stress developed in the walls of the tank. That has to be determined here. So radially, the liquid wants to expand the tank. The tank, what happened, is under stress now. So who will balance this force? So this tank, the radial outward force is there. So therefore, I'll assume now a plane diagram. So shall I say here, the liquid will exert a force. So that pressure into area. So I'm going to assume a cap actually. So that cap is what you have to bring it like this here. Where you have come across diagram similar to this in surface tension. This is the part of a strip. This is a strip on tank. I'm shading it at least by looking at this, you should assume that one. Football patch, how football patch will look like this, you have to assume a patch. Let's get into the thing, that one here. So how the forces will be acting, you know. So here T, so this length is L, and the thickness is what? Here, this one. Able to understand now? This one, the thickness. So who will balance this force due to the tension setup? The pressure force will be acting upward here. Let S is the area of the strip, delta P into S. And that is balanced by component of tension. So I'm just converting this into plain diagram for students to make them understand. So here is delta P into S. This is some alpha, you take it, because theta is what change in temperature is telling. So let this be alpha, this alpha. So like that, this is what, like what I'm showing is like a 1, 2. That 1, 2 is what visible for you. Able to understand? I'll give some color for it. That is what this one. I have to show still that brown color only. That is what this one. Okay, let's directly get into this one. Now, delta PS will balance this force exerted by the liquid component of tensions. So the equations will be 2 into 2t sine theta. You have to ask question. Okay, 2t sine theta. Okay, fine. 2t sine alpha. Vertical components will balance this. Why this 2? Anybody? There's a strip. Actually, you are here looking at these two forces. Even these two forces also will come, no? So vertical component of these two is what? 2t sine alpha. Even vertical component of these two also will act vertically down. So therefore 2 into 2t sine theta. 2t sine alpha. Agree this? This 2 is very important. It'll be like this. Huh? There's a patch. The component of these two forces is 2t sine theta. Component of these two forces also 2t sine theta. Everyone agreed means I'll proceed. That's all, only calculation. Nothing is there. So this alpha, this strip will be very small. So therefore this will become delta P. What should be the S as it is? Area of the strip it is. S is equal to 4t alpha. Let me write here. Now, what is the 2t 2 alpha? Okay, I'll write all this. So let it be here. 2t alpha. T I'll bring outside. 2 alpha. Anything can you write 2 alpha? L should be equal to R into 2 alpha. Arc length. This is the arc length. So therefore 2 alpha, what you can write? L by R. Till here, okay? 2TL. So what is this bulk modulus? How you define bulk modulus? Okay, we'll write it here. Equal to delta P by change in volume by original volume. So what is dV by dV? You can write it as gamma delta theta, change in temperature. Volume expansion of gas, fractional change in volume, gamma delta theta. So therefore this delta p, what we can write? B gamma delta theta s equal to 2TL by R. What is S? We should write area of the strip, which is equal to L square. So B gamma delta theta L square. So finally, what is the expression for tension? B gamma delta theta L RL by 2. Is asking the tensile stress. How you define tensile stress? So here only we'll go for it. So this is what that yellow color strip I'm taking. Thickness is T, length is L, and the tension T is acting here. So tensile stress in the tank. Now let's come for this one. Tensile in the tank. So what it should be equal to? This should be equal to tension by area. L into T will be area, no? So let's write T. What is the expression? LT B gamma delta theta RL by 2. So B gamma R change in temperature by 2T. Delta theta is or theta. Change in temperature. What is delta theta? Something is bringing some elasticity into the picture, little bit. Bulk modulus idea. Football, best example, football, as you keep on increase the air in the football. So definitely what happen, the patch here, the one patch is there, no? The patch what happen will exert, will experience a force of like this. Better you take balloon and as you start blow air, so you draw with marker pen, draw one strip like this. Then you see that definitely what happen, the forces, you at least you can see that one. The adjacent things will try to pull that particular patch. Best example is football, no? The stitches which are there, they'll become taut as you keep on increase air. Initially with no air, the stitches which are there like this, no? They'll be loose. As you increase air open, the stitches will become taut. So the stitches here will exert a force like this. Make observation. Take football. Make observation. So many objects are there, no? Where of this particular situation you come across.